All right, next up we have Chris Jenkins from Sandia. So Chris is a principal cyber researcher and development staff member at Sandia. His current focus is in three major areas: cyber physical systems research, space cyber, and cyber research outside of the lab. And today he'll speak to us about moving target defense for space systems.
So thank you for that introduction. And I guess to also add to that, I just recently became a first-time father of twins about a month ago. Thank you. So I had probably the best sleep I've had in the last month last night. So, but this work was actually done primarily at Sandia with some support from Purdue University during our last year. This came from an actual research report. And I apologize, they have me with a PDF that doesn't seem to want to play nice right now. Okay. So we'll go into kind of a little bit about the intro and some of the background and why we did this work. Since this is data work, so I'm going to focus a lot more on the data side of it. So I'll focus more on the algorithm and experimentation. Finish up with the work that Purdue did, some machine learning attacks they did against our algorithm, and then also look at the ways that we believe we can apply this algorithm for other ideals within the space domain. So what I was saying is that Wright-Patt Air Force Base in Dayton, Ohio, I think back in 2015 or 16, came out with a report that wanted to highlight what you can do on a 1553 bus, so similar to the first talk we saw here. And in particular, they were focusing on reconnaissance or exfiltration, as well as potentially replay attacks and whatnot. And so at that time, I was starting to look at honeypots, deception, I think MTD. And so the idea came out is, can we actually apply moving target defense to a real-time network? And so kind of the bottom line up front, we were able to show that we can reduce adversarial knowledge by 97%. And so our goal isn't to say that MTD is the thing to use for all particular attacks. It's just to say, can we use it? And if we can, what does it buy us? What does it give us? And so I'll tell you a little bit about Sandia very briefly. So I think DOE has 17 national labs. We're under the National Nuclear Security Administration. And so Sandia has two sites. I guess this is a PDF, it doesn't work. But one site is in Livermore, California. One site is in Albuquerque, New Mexico, and I'm coming in from the New Mexico site. And this work has been funded under the Stark's Mission Campaign. And so a mission campaign at Sandia is a way that we put forth money, in this case around $35 million, over the course of 7 years into areas that we think are going to be a challenge for the United States. Down the line, we want to get a head start on trying to solve these problems. And so in our case, this work is funded under cognitive analytics. And so looking at ways that space systems in the future could have what we call, instead of artificial intelligence, artificial instinct. So think about putting your hand on a stove, your hand jumps back before your brain recognizes it. So how do you design systems in the same way? Looking at both algorithms, electronics, and sensor layer protection. So moving on to the background. So cybersecurity, it's pretty much the field I came into. And a lot of times we think about how do I create this perimeter? But once you're in the perimeter, you kind of can have fun all day. And so we kind of move now to cyber resilience, which is even if you get into my perimeter, even if you attack a system, can you, in some sense, have graceful degradation and hopefully recover your system so that the attacker is pushed out, hopefully outside the perimeter, or at least push the attacker where you want them to have a difficult day. And so, going back to FRL RYWA, I believe is the director that created the report, we wanted to look at high consequence systems. And so when I first started this report, this work, this is when I think the Crow's office was being formed. And so 5053 is using a lot of military avionics. Like that's really what it's for. It came out in the late 1970s. But it's also used in space systems, so it made it easier to pitch it to this particular mission campaign. And then also, it's also used in other high consequence systems. So in general, we just wanted to understand if we want to apply moving target defense to HCS or high consequence systems, what are the challenges? And then two, what does it buy us? And can we support that with facts and with data in a quantitative sense? And so for I guess quick show of hands, how many people have heard of moving target defense? Okay. So the way I like to explain it, kind of going off script, what's on the screen, is that if I want to break into someone's house, right, I'm going to look at how many windows you have, how many doors you have. I'm going to see how they go in and out, security cameras, so on and so forth. But if on Monday I came over to your house and you had 2 windows up top, 1 at the bottom, and 2 doors, okay, I'm going to take a picture of that. I'm going to see that. But if Tuesday, now that door is on the side, instead of 2 doors, it's 1 door, you now have 15 windows instead of 2, and the security cameras have moved around, and that changes on Wednesdays and Thursdays, so on and so forth. Effectively, that's moving target defense. The cameras, the windows, and the doors are your moving target. And, of course, the defense is the fact that as an attacker, I want to move somewhere else because I don't know on Saturday what your house is going to look like. And so same concept here. In this case, it's a IP address that's moving around, but the attacker's having a hard time accessing the real IP of the real server. And so, once again, our question is, if we want to use moving target defense, but we want to apply it to a real-time protocol, in this case, it was 1553 and SpaceWire. But unfortunately, this happened during COVID, and so we had to reduce what we were looking at, so we just went after 1553. And so, of course, the 2 key research questions: can it be applied in a manner that maintains operational constraints, so we don't affect the actual protocol? And then 2, can we actually have quantitative as opposed to qualitative evidence that it does indeed improve the cyber resilience of the system? And so now, giving you a quick overview of 1553, but not to spend a lot of time on it, it's a command and control bus. So for the point of this talk, we want to look at the bus controller, the remote terminal, and the bus monitor. And so the bus controller sends out a command on the bus. As mentioned in previous talk, you have bus A and bus B. The remote terminal is going to respond to that command. To say the appropriate remote terminal is going to respond to that command. For this particular architecture, remote terminals can have the address between 0 to 30, with address 31 being a broadcast address. And then the bus monitor just records all traffic, so think of it as a flight recorder that you may have on an airplane. So diving down a little bit more, but once again, still staying at a higher level. So here you have what's called a BCRT message, or a bus controller is sending a command to the RT. The key point for our particular talk is where you see the 3-R-1-32. So the first number 3, that's the address of the remote terminal. And so what we wanted to see is that if we change that address dynamically, how does that help with stopping the attacker with reconnaissance? How does that potentially prevent replay attacks, so on and so forth? And so I won't go over all the design challenges, but I think the first one is important. We thought about, should we design a 1554 or something else, right? And speaking with WritePat, speaking with some of the people in that office, RIWA, it was very clear that that was not the way to go. And so our first thought of this algorithm was, how do we do it where it's on top of 1553? All the tools that you have, all the companies that work with it, you can still utilize their software and hardware. And then, of course, I think the second one is, how do you actually change the address such that you don't have conflict, you don't have collisions, so on and so forth. And, of course, the other 4 there that you see. And so at that time, it was patent pending. Now we've been awarded the patent. And so we're going to go over the novel MTD algorithm for 1553. And then towards the end of the talk, we're also going to show you where other places that we feel like we can use this algorithm, not just only 1553. So the algorithm at a very high level, we're going to use a shared key and a nonce, or number used once. The randomness primitive, it's about 4 steps inside of that. Before this talk, we're just going to call it a randomness primitive. And what comes out of it is a randomized array, or randomized, to say, ordered array of numbers between 0 and 30. And then also what comes out is another nonce. And so, of course, you can see that you can feed that nonce back into it, produce another randomized array, produce another nonce, and you get to what we call the state matrix. So in this case, every single array that you produce becomes a column, and then we label each column with an index. And so the way that we utilize this particular array, we have different ways that we can index into the state. So one of the methods is called static offset. And so the way that it would work, if you had a remote terminal that has a static address of 0, the bus controller can send out an index value of 3, so the new address would be 4. If a remote terminal had a static address of 4, using that same index, its new address would be 24. And since it's a unique ordering where none of the numbers repeat, you're guaranteed that every remote terminal is going to have a different address. And so we also looked at a different way that we could do this. And unfortunately, this is a PDF, so I actually had a nice animation here for this slide. But you can see on the chart on my right side that if you have that same scenario where you start at an address of 0 and the index of 3 comes out, your next address is 4. But unlike the static offset method, now you have an address of 4, index of 1 comes out, you move to 5, and so on and so forth, as you see in this table. And so your next address goes from 4 to 5 to 1 to 16. And so one of the differences between the static offset method and the current offset method we saw is that the current offset method moves up more around in the state. And so the question becomes, how can you quantitatively prove which method is better? And so we'll get into that in a couple slides. And so we also looked at, so this is nice. You can generate a state matrix. That's cool. We want to use it. How long does it take to actually generate it? And so this was on a 6th generation, I believe, Core i7. And so for 65,000 columns, it takes about 19 seconds. So while you may have 19 seconds during initialization, we believe that you would want to have something that's quicker, preferably under a second. So you probably want to have something around 128 or 256 columns. And so the question becomes, well, which one is better? Is having 65,000 or having 128? Because having 128 is definitely going to be faster to generate your state, but do you have the same security? And we'll get into that in a couple slides. And so looking at the same processor, if you want to generate 65,000 columns, it takes around 283 microseconds. For those of you who are familiar with the 1553 bus, you know that every bit is 1 microsecond. So this is not something that you probably would want to do on the fly. It's potentially something you actually want to generate ahead of time. Though there are ways you could potentially generate on the fly, but our recommendation is to generate it ahead of time for your particular system. And then the size requirements. So one of the things that we wanted to take a look at, not everything, is going to be, even though we did I'm going to call it the performance numbers on the core, I think i7 6th generation, not everything is going to necessarily be a processor. Some are going to be microcontrollers. Some are going to have nothing more than a megabyte of memory, sometimes less. And so we can see here that for 65,000 columns, you're going to need 2 megabytes, but for something around 64 columns, you can get away with 2 kilobytes. So it's something that could be put into smaller or embedded type of systems. So I mentioned earlier that you could do 65,000 columns, but that would take you 19 seconds to generate everything. And so we did a histogram, and we found out that even if you have 256 columns, which would take you less than a second to generate, you have a similar entropy results that you would for 65,000 columns. So we can say with confidence that generating a smaller state matrix still gives you hopefully similar security guarantees. But we wanted to go a step farther. And that step farther was looking at unpredictability metrics. And so for this particular chart, I could probably spend another 10 to 15 minutes on it. But the point I wanted to highlight is that Indu, who actually did the work for this chart, she looked at 9 different unpredictability metrics. And what she wanted to understand is look at 3 different variables that she wanted to change. 1, how do we index into the state matrix? So static and current is what I talked about today. There's also linear static and linear current. She also wanted to look at the size of the state matrix, which is the second graphic we have here, and as well as look at what she called the state matrix update period, which is, in this particular case, after every 32 index values, I'm going to generate a new state. And then every 32 again, generate a new state. And so seeing that if changing your actual state matrix, does it actually increase or decrease the unpredictability? And what she found out, at least in our case at first, changing the state matrix actually doesn't change it being more predictable or unpredictable. Of course, 1.0 being highly unpredictable, closer to 0 being highly predictable. The second graphic actually agrees with what you saw previously, is that even though you change from, in this case, I'm doing some quick math, 256 columns up to 65,000 columns, the metrics don't really change that much. So you could produce smaller state matrices, which actually agrees with the previous slide. But then the thing that really stood out to us is that the way you index into the state actually had the most influence. And so you can see for one of the metrics, you have here around 0.6, I believe that's the transition turbulence. As you go from static to current over to linear static, linear current, it actually improves. And so once you get to the machine learning attacks that Purdue did, that will become more evident why that's the case. So we wanted to move on to experimentation. And so when this work was first started, we did it through what's called Exploratory Express. So think of it as a little bit of seed money to try out your idea in the hopes that you can get further money down the line. So the first summer that we did this, I believe, was in 2019. I had 2 interns come to work on this project. Both went on to become full-time at Sandia. But we wanted to start out with something simple. So could I do something, of course, the students can understand, but calculate the Fibonacci sequence with and without MTD, using actual hardware from, believe it or not, Alta DT. They're actually one of their offices are 30 minutes from the lab. So I've actually been out there and done some training with their engineers. But we bought 2 of their devices, constructed a 1553 bus, and wanted to see could we calculate the Fibonacci sequence by changing the address versus just having all the addresses be static. And then the second part, which really came from the paper that RYWA at Wright Pack gave to us, and that was if I wanted to exfiltrate data, so I had a particular remote terminal that I'm interested in, if I change the address, what does that do, hopefully, to the adversary in terms of the amount of information that they can gain? So those are the 2 key experimentations that we did. And so kind of a real quick overview of how it works. So the bus controller is going to send out what we call MTD start command, and that can change the nonce that I talked about earlier. The RT is going to create a hash of its state, send it back to the bus controller, and then as long as the 2 match, the bus controller knows that both devices have the same state. And we could have had more RTs, but we wanted to make this as easy as possible for the attacker. Our assumption being that if we make it easy and we can still prove it's hard for the attacker, having more remote terminals is probably going to even be harder. Then the BC starts to send out 2 numbers. RT sends back the answer. You do the calculation. And then and we call that a frame. So you see the 1, 1, and the 2, that we consider a frame. And after so many frames, the BC sends out an MTD update message with the index value. The RT updates its address, and you continue, and you get to B520, which is the 24th Fibonacci in hex. So why do we stop at 24? Anyone want to take a guess? I'm looking at the 1553 people. So it was the largest unsigned number that we can put into 16 bits. Because I wanted this to be easier for the interns and not having them try to stitch words together. So we want to make it as simple as possible to get our results. And then once quick again, these are the commands we came up with. So just to kind of show a little bit more detail. So you have the nonce and the MTD start command, the verify, so you have a hash of the state. So that was just a way for the RT and the BC to agree that we have the same hash without actually disclosing the matrix on the bus. I probably would in the future use something like an HMAC or a keyed message authentication code to add some more authenticity to it. You have the MTD update message, which has the index value, in this case 17 hex, and the B520, which is finished. And so what we're really looking for is, and I have it circled here on the slide, once again, the 1-R-4-2, in this case, the first number is what we're interested in. So we have a remote terminal address of 1, send and receive. Message number 15 in this case, you have a broadcast with a hex value of 17, and then the RT changed its address from 1 to 27. And as you can see, there's not any, particularly any errors. It actually just went from 1 to the broadcast and then went to the new address. And so when we get to the Purdue work, what we want to figure out is, can I, as an adversary, listen on the bus and do a data capture and figure out that if I have a remote terminal address of 1 and I have an index value of 17, can I, as an adversary, figure out that the next address is going to be 27? So once you figured out that we could do the Fibonacci sequence with and without MTD, then we wanted to say, okay, if I'm an attacker, I want to exfiltrate data from a particular device, what does this MTD buy me? And so we took a laptop with the Ethernet switch, had 2 1553 devices from Alta DT to construct our bus. And so as before, we have a host node and a participant node. So think of that as the bus controller and the remote terminal. The listening node is just your bus monitor. And then we have a secondary device, which is, or in this case, really secondary bus monitor, which is just listening at a particular address that's based on our scenario. So once again, I had some transitions, but on the left side in this particular scenario, we wanted to see, okay, an attacker is going to pick a random address. It's only going to listen at that address, but the host node and the, going back to the previous slide, the host node and the participant node are going to still do the Fibonacci calculation. So everything here is doing the Fibonacci calculation. We just want to see what information the attacker gets. And so if the attacker picks a particular remote terminal address, and we change the frequency at which we're going to update that address, we see that pretty much across all frequencies that the attacker had a reduction of 97% of information that came out, or 3.2%. When you think about this, it makes sense. What this really says is that the amount of time that the remote terminals at a particular address is equal for all addresses. So effectively, it's no different than, someone call it random, but really is no different than picking an address and listening at that address. And so on the right side, similar situation, but in this case, we assume the adversary knows the remote terminal of the device is looking for, or I should say it starts at that address. And so what we realize is that if you look at, in this case, frequency decreases as you go from left to right. On the right side, when you're approaching, or in our case, 100 frames per between addresses, you're spending a lot of time with the known correct address. And because our experiments were pretty short, in this case, 50 generations. So what is a generation? A generation is calculating the 24th Fibonacci number. Because we did it so quickly, we needed a way to generate more data, and so we just kept doing it over and over again. And so if you change that to, say, around 5,000, 500,000 generations, we would predict that the actual graphic on the right would match the graphic on the left. But because you had a short amount of runtime and you started at the right known address, lower frequency changes allows you to collect more of the data. Of course, once again, if you go back to high frequency changes, the adversary does not get as much of the data. So we wanted to actually look at a smart adversary. So let's assume in this particular example, we had a frequency of 25. So every 25 frames, we're going to change the address. But the adversary can learn, in this particular example, the new address in 8 frames. Then you can exfil 70% of the data. 16, you can exfil 40%. And so one thing that it kind of told us or taught us is that if you're going to have something like MTD in your system, how fast can you change it? If the adversary, if it takes a lot of resources to change it, then maybe MTD isn't right for that system. And that's okay, but that's what we learned from this. But if you can change it fast, then it may be appropriate. So it starts helping you with informing design requirements. So if I was looking at 1553, one thing I would say is that as long as you can generate your state ahead of time, you can put the index on the actual bus, and then you can change your address in real time. But once again, if it takes you a lot more of the resources to change your address, the MTD might not be the way to go. And so we'll finish up with machine learning that Purdue wanted to do. Once again, this came out, unfortunately, COVID came out during this time. And so some of the things that we wanted to do with them, we kind of had to push to the side. But I think the key, the most important one that we felt was, can you determine the next address? Because if you can, algorithm is game over. And so the model that they used for this particular work was LSTM model. They varied the training size, but they kept the test size at 20%. And so I am not a machine learning expert, but I was taught what F1 and MCC stood for and why it was important. So as the closer you get to a value of 1 for the F1 and MCC score, you effectively have broken the algorithm. You effectively are predicting the next address correctly every single time. And so we looked at 2 methods. Once again, the static offset method and the current offset method. And if you remember from the chart I showed, some of the metrics improved from static to current. And so we knew it improved. We didn't know what it would buy us. And so when they did in machine learning, this will show you what it bought us. And so we have 3 charts. They look very identical. So going from left to right, the big difference is that when you see 1, 1, you're looking at the current index value and the current address. 2, 1, you look at the previous the previous address, the current address, and the index value. And of course, 3, 1 is 2 previous addresses. And so as you can see, they effectively broke the algorithm, right? And so the students were ecstatic. They were happy, jumping up and down. Like, you know, I destroyed the national lab. I'm good, right? And so, of course, unfortunately, you guys got the PDF. And there's an animation that revealed that when we changed one line of C++ code, it went down from 0.14 to 0.2. So effectively, it became random. They no longer broke the algorithm. And given them more and more data, they had a big challenge of trying to break it again, and they couldn't. And so I kind of just smiled at them when I received them. And the key takeaway is that because we're using more of the state matrix, it's harder to then do that prediction, because in the static offset method, there's a one-to-one correspondence. For a given index, I'm always going to have the same next address, and that will never change for a given state matrix. With the current, you have this kind of temporal locality of what is my current address, and then that affects the next address. And so in that case, the charts look similar, but on the y-axis, it was 0.4, I think 0.14, I think 0.18, and maybe 0.2. So a lot worse at that point, no different than random. Like I said, I wish I had the animation PowerPoint here. So we'll finish up. So this was done for 1553, definitely successful. But as we started to finish the work, we realized that there was a generalized structure to the algorithm. And we won't get into it. I'm free to talk about it outside of this talk. But there's 4 components that came out of it. And so from that, we felt we could apply it to other ideas. One of those ideas was IPv4 random port generator. So there's some technology at Sandia called ADSEC. It's used for more or less encrypting the TCP port numbers for TCP IP communication for industrial control systems. And they used a key to do the actual encryption on the port for all packets. So one key was used for all packets. By being able to integrate this idea into that particular technology, we can now use a different key per packet. So we can make it a lot stronger. And we had a non-disclosure agreement with a commercial company to actually integrate this into a MTD technology that they're using to push to the U.S. government. The second idea that we had was a two-factor authentication passphrase generator. The concepts for this would be if you wanted to execute on a satellite some highly sensitive or critical commands, you should not just execute them, right? There should be more authentication. And so what we wanted to do is the satellite would generate a challenge, the mission control or the ground station would issue a response, but that challenge response would be based on the state matrix that you generated. And so you may not need some of the IT infrastructure that is typically associated with RSA tokens and other type of authenticators. And of course, if we wanted to do this, we have to update the state matrix to represent passphrases. 0 through 31 is probably not going to work anymore for that type of system. And then the last one we wanted to look at with that same startup company is a transparent file system for ransomware. So for those of you who study ransomware, typically the system files aren't touched because you still need a boot to show the ransom. But you typically look at, documents, PDFs, pictures, so on and so forth. But if you can't see it, you can't encrypt it. And so could we use the state matrix with a file system to actually reveal the files when needed? For those of you who've done Android applications, it borrows some idea from the fact that every app has a different view of the hard drive, whereas in your typical desktop systems or laptop systems that you have, all apps can see all the data on the drive. And so we wanted to look at a way to implement this to where at times you can see the whole hard drive, at times you can't. And how does that, or could that protect us more against ransomware? And so with that, thank you for your time, and I'll take any questions.
Time for 2 questions, so those 2. All right.
So for the 1553, I understand intrusion prevention, real time, trying to, as a rogue bus controller. That makes perfect sense. I'm confused about the exfiltration because with the data rates of 1553 and you're limited in the number of RTs you have, why wouldn't you just exfiltrate all the data and then solve it offline?
So that is a common question that comes up. So you can pull off all the data. The question becomes then, if you're pulling off all the data and you wanted to potentially do a replay attack, so number one, I'm going to confuse you as how many RTs are actually on the bus. So for ours, it was 1 RT. If you look at the actual data that came off, there's 31 RTs on the bus. Number 2, assuming that you can look at all the data and you can figure out and fingerprint, now when you want to do your replay attack, you still have this concern of, I got to replay with the right address. So once again, MTD is not going to necessarily fix everything, but we're going to make it harder for the adversary and make it asymmetrical, so it's easier for us, harder for the adversary. Good question, though.
Hey, good talk. Thank you. I think this is one of the areas you weren't able to study, but if you comment on it, it seems like if this technology were implemented widely, the goal of the adversary would be to get access to the state matrix, and then you've solved the problem. So maybe if you just comment on how that would be possible or avoidable.
Sure. So we actually were going to run the DLL that we had for this and actually at WritePat. I think the week the government shut down, so kind of derailed that. And so one of the ideas that we had is, could you just listen on the bus, and over time, could you build up the state matrix? I would argue that you probably could in the static offset, and it might be a little bit harder in the current offset, but just assume that you could. We can rekey fairly fast, create a new state matrix, and then the one that you listen to is no longer valid. So hopefully that answers it.
Well, let's thank our speaker again.
Thank you.